So tonight, what I'd like to do is present a topic that I know I skipped over when I was starting my journey in quantum computing, thinking that, oh, it's no big deal. But I quickly got humbled and discovered that essentially complex numbers are used throughout physics, and therefore by extension throughout quantum computing. And it's actually a very simple topic, but if you haven't thought about complex numbers, or you were taught it decades ago, or you've never been taught complex numbers, which is certainly a possibility, it's really one of those things that just kind of confounds you when you read the quantum computing books. So that's what tonight is about. It's really the beginning of a journey, the beginning of a set of tutorials, if you will, that I plan on creating and sharing with you in the meetups. And so quantum computing relies on complex numbers, as you can probably imagine. So tonight, my goal is not to razzle-dazzle you with all this technical stuff or large amounts of information, a lot of mathematics, etc. My goal, and I think is an important goal, is to really take our time, go through it slowly, and make sure literally every one of us is comfortable before we move on. And those of you who are totally familiar with complex numbers, oh yeah, thanks. Increase the font size. I knew I was going to have to do that. Let me see, I forget how to do it in this thing. Yeah, it's right down here. There we go, thank you. And also, if you haven't noticed, I'm trying to use Word instead of PowerPoint. Frankly, I get a little burned out from PowerPoint. So I'm going to try using Word, where I actually created this document for tonight. And then by the way, I'll save it in the usual places with the annotations on it. So anyway, we're just going to go through this slowly. And first of all, I think an important thing to get your head around is, you know, what's the whole idea behind complex numbers? Not necessarily what they are, but hold on. I hear two voices from the same recording. Let me see, that's a possibility. Hold on here. Well, I don't know where that's coming from. Are others hearing two voices? I hear three in my head, frankly. Two's getting better. Okay, so it could be just a local problem. All right. Sounds fine. All right, thanks, Jim. Yeah. So anyway, you know, let's just step back and go through this slowly. And so I'll be a little not off subject, but really, you know, what from a high level, what is this magical world of numbers that we work in? Then I'll walk through what is the case for using a complex number or an imaginary number. Most of you may recall it as that I, which is in short, I equals the square root of -1. I'll just cut to the chase. After we set up what it's for, I'll cover a few of the details then. We'll talk about what's known as a complex conjugate, which is used all over the place in quantum. We'll talk about the absolute value of a complex number, also referred to as a modulus. Then we'll cover what I like to call the four amigos: addition of complex numbers, subtraction of complex numbers, multiplication, and the seemingly odd notion of division, complex numbers. And, then I'll just walk through a little bit of Python. I'll just expose you to Python and how it covers complex numbers. I'm not going to go into this deep. I just copied and pasted literally a couple good sites that had, it all listed out there in a very understandable way. And then, take about a minute or so to talk about next steps and maybe a next talk coming on down the pike. So let me move on here. I am doing two things at one time, three things. It's kind of hard. Excuse me. Oh, and by the way, so this is really, I really want this to be conversational. So by all means, if you've got any questions, I've got the chat in front of me. I'll look at it periodically. So ask away, and by all means, we don't want to go any further until each of you really is comfortable with this and understand what I'm saying. And this is frankly, I'm not a math teacher, so this is frankly really the first time I've tried to describe complex numbers to someone else, and that's always a difficult thing to get right the very first time. So you folks are my guinea pigs. Thank you very much. But I hope it's understandable. So let's just start with numbers. Here's two links to a real interesting story that I saw in thinking through numbers. And, numbers actually evolved. We didn't wake, most of us woke up and had our first math class in whatever grade it was, and, numbers were just there. But I think understanding the story of how our numbering systems evolved has a lot to do with really helps understand what the purpose of complex numbers are and why they exist. So I think it's worth covering, and many of us maybe never even looked at complex numbers in this light. But these two articles here actually point to a tribe, I think it was in the Amazon area, that when the scientists or the researchers discovered this tribe, they discovered that they only could count to 2. And after 2, they had a word meaning many. And interestingly enough, whenever they said the word, whatever the word was, they would refer to their hair. And so they had 1, 2, and many, and that was their numbering system. And the main takeaway from this story, from this tribe, is that in their world, their worldview only involved 1 or 2 things, or more than 2. They had a very simple society, and they didn't need pi or complex numbers because it just wasn't something they needed in their world. So the point is that over time we've extended, our society has extended our numbering system as our world became more problematical. And I originally had the word complex here, but I think that's inappropriate given the subject matter. So as our world became more and more complex or problematical, our problems started to become more and more sophisticated, we essentially started to need to solve equations, if you will. And the equations would become more and more complicated and more elaborate as societies evolved. Now, when it comes to numbering systems, we expect our various numbering systems, the mathematical folks, and I'm just beginning to understand this after 60 years, really insist on closure when it comes to these types of operations. Enclosure means that if I have a set of numbers and I perform addition on them, I should be able, the answer should be in that set. Or if I operate with subtraction of two numbers in a system, the answer should be in that set of numbers. So they had a problem here, right? If they took 1 and added 2 to it, well, I guess the answer would have been many, which would have been, I guess, the same as, well, come to think of it, yeah, I guess you could do 2 plus 2 equals many. So in their system, you know, it wasn't necessarily closed. I guess it was closed, but subtraction, it wouldn't be closed here because you could get answers that are beyond many. So this is an important feature of numbering systems. And again, I'm not a mathematician. There's probably a better way of describing it. But the point is that you really need to do these 4 things in a numbering system that's functional. Now, in school, most of us, I believe, were taught these various sets of numbers. And it basically started with, you know, probably kindergarten, where we had counting numbers. So our world, when we were super young, consisted of 1, 2, 3, 4. In other words, 4 apples, 3 apples, 6 bananas, and things like that. And that was fine if you're a kindergartner kid, because all you cared about were getting those 2 apples from your mom, your teacher, or your parents or whatever. Then actually I think we credit the Indian culture for recognizing that, hey man, we need a 0. And that's a really interesting story as well. I remember seeing a program a few years ago on the history of 0. It's quite interesting. But we'd be in trouble if we did not have 0. So that's known as the natural number system. And you've probably run across that before. And by the way, you know, mathematicians like symbols, so they have this n to represent this numbering or this set of numbers rather. Then we got a little more sophisticated, and you know, I'm not sure of the history of negative numbers, but think about it. In cavemen days or cave women days, you know, you had 2 apples and you got 3 apples from the other family, and you now have 5 apples. And the notion of having 5 apples and taking away 6 apples from them, I doubt existed in prehistoric man days. So I suspect when people started, this is my suspicion, when we started doing economic trade and when money started to occur, in other words, banking started to occur, frankly, I think that's the only reason we started dealing with negative numbers. And, you know, you can't have banking without negative numbers now, can we? But notice it went from apples to banking. And next, we started running into situations where, you know, 1/2 apple, 3/4 of an apple, etc. And so we have the rational number system, which is a set of numbers. And believe me, I'm trying to avoid mathematics, but I do understand that, you know, being precise here is really important. And I think it's good that we do understand mathematical representation at this level. But rational numbers are essentially those numbers that are in the form of m over n, where m is a integer and n is a positive. Oops, I got a mistake there. That should be essentially a non-zero number. You guys know this, so. And then finally, probably in high school, maybe junior high school, we started to get into real numbers. And those are numbers that we find very difficult to come up with solutions. And that's e, pi, square root of 2, and all that kind of good stuff. So Wikipedia, and I didn't really, I did, yeah, this was a last minute entry here. Wikipedia does have a page on the table of mathematical symbols, and it's in order of introduction date. So if you get some spare time sometime, take a look at it, and it's interesting because they go through the symbols and what decade, et cetera, what century these symbols were invented in. I didn't correlate what's on that page to here, but I hope it's fairly close, at least chronologically. I believe the real numbers, yeah, irrational. Yeah, you know, folks, so the comment is, I believe the real numbers in the table should be irrational numbers instead. To that point, I did notice a lot of inconsistencies in how we refer to these sets of numbers, actually, because I did see it listed in some places as real, and I do recall irrational. In fact, that's what I'm tempted to say, irrational. So there is a fair amount of mixing terms here, and I didn't think it was worthwhile to really dig into it and discover exactly what the scientific and correct term is. But that's something I definitely need to delve into later on. But it's really what I'm trying to do. What's important here is not necessarily these details, not to cover my mistake here, but it's the story of we are building up our number system in conjunction with our lives and our the equations and problems that we're trying to solve. As they become more complex, we need mathematical numbering systems to reflect that complexity and to be able to deal with that complexity. So, one takeaway of that chronological list there, roughly, is that you want to think of it as, sets. So we have the natural numbers, which are a subset of the whole numbers, which are a subset of the integers, which are a subset of the rational or real irrational numbers, etc. So we're essentially making numbering systems that generally contain the prior numbering system plus some other goodies, plus some other goodies, plus some other goodies, etc. So, all right, now let's take a look at those numbering systems again. And what's really powerful with numbers is that we have a way to graphically, in a picture, illustrate what those numbers are. So, and many of us are visual, so you may think about it in this way. So when we were kids, we had a number line like this, and this is, I think, how many of us learned to add. So if I take 2 plus 3, I have 2, and I move over 1, 2, 3, and there's my answer. All right, wonderful tool when you're a kid. Frankly, at this age, sometimes it becomes valuable to get a number in line like that again. Now, when we moved into integers, z, again, I question that. But when we started needing negative numbers, we now went to, okay, so 2 minus 3. So we go here, we go 1, 2, 3, and we got negative numbers. All right. Now we got into rational numbers. Now our number lines and our illustrations of those numbers, our graphical representation, got a little bit more hairy here. No, I guess it does look like hair. And then the real numbers, the same thing. So we have this graphical representation of our number sets, okay? Now let's start setting the case for the imaginary I, the dreaded I. And again, this is correct or incorrect. It's a copy of what we saw earlier. And notice here, I put in a column of equations. So frankly, I had trouble with this one, but these were pretty straightforward. So some of the equations we had were x plus 7 equals 0. What is x? 4x minus 1. As we go down the list here, we're getting more and more complex. So finally, we got x squared equals 2. And so x becomes the square root of 2. Good? All right. Now, what about solving something as simple as x plus 1 equals 0? Well, that's child's play, right? It's x squared equals minus 1. Uh-oh. Here is where many of us stopped in math. My school, I don't recall learning anything more than, okay, well, x squared, or x equals the square root of x equals I, and I equals the square root of -1. All right. Anybody not see this before? All right, that's probably where most of our, 98% of us have kind of stopped. So let's continue on here. So this is why we have complex numbers. Essentially, we need to solve this equation here. Solve for x. All right. So let's start with what's the standard form. Well, let me skip that. Let me go right to here. So if we agree that I is a square root of -1, and it's no different than saying a equals 2 or b equals square root of 3 or 4, something like that, we're just going to say wherever we need square root of -1, we'll just replace it with I. All right, so that's this guy right here. Now, an interesting phenomena is if you take a look at it, I to the 1 power is I, no problem there. If you square it, what is -1, square root of -1 times the square root of -1 equals what? Square root of -1 squared, which equals -1. So I squared equals -1. I cubed equals -I. Think about it. Try it out. I to the 4th equals 1. Now what's interesting, what's cool, is this pattern repeats. So this is the same as I1, I squared, I cubed, I to the 4th, etc. Right, so that's one of the things that's just kind of, it's kind of cool. You've basically got a repeating phenomena here. And what was really comforting is when you think about what is I to the 0 power, what do you think it is? It's 1, right? So it follows the pattern. I to the 0 equals 1. And I begin to wonder, frankly, again, I'm not a mathematician, but I begin to wonder if that's why, if complex numbers are why we say I to the, or x to the 0, anything to the 0, 4 to the 0 equals 1. It might be, I'm just guessing, but it might be because of this pattern here. All right, so we're going to invent complex numbers. I is the imaginary number. So I have a complex number here, and here's where it's going to get weird, and this is why we don't necessarily learn it in grade school all the time. This here is a complex number where A is an element of, essentially it would be a real number, and B is an element of the real number set as well. So that's this guy right here. So a valid complex number is 4 plus 5i, or 2 minus 3i, or minus 4 plus 6i. All right, oops. So it's got two real numbers as well as the I component. All right, it's fairly straightforward, well, sort of. So I found this little quote and doing some research about this, and I thought it kind of resonated, and frankly, I haven't thought about it deeply to see if it makes total sense. But let me read it to you, and in the context of quantum computing, I'm really curious about this. So anyway, the interpretation of complex numbers is easy to grasp. Complex numbers are numbers that have a sign that is neither all positive or essentially negative, but it's something in between. You know where I'm going with this, AKAs. In other words, sign is not a binary concept, but a continuum. So it just kind of reeks of superposition, which I'm sure most of you, if not all of you, have heard about. And I'm just really curious, I want to delve into this a little bit further, if is the tie-in between just complex numbers in general and physics use of superposition and all that good stuff. Now, remember back when I was talking about being closed within multiplication, division, addition, and subtractions, etc. Complex numbers are closed. And this is a comment I read somewhere about complex numbers, so it's only one place I saw it, but every equation, if that equation has a solution, has that solution in complex numbers. So let me just try to think about that in a very simple form. The number 4 plus 3 equals 7 could actually be thought of and is a complex number, where this is the same as 4 plus 0i plus 3 plus 0i. So clearly 0 times anything is 0. So really the numbering system that we've been using our whole lives, the simple real numbers or rational numbers or natural numbers, are indeed a subset of complex numbers, because all of those numbers can easily be converted into a complex number, and in fact they are complex numbers. It's just that in the a plus bi, our entire lives we just plugged in a 0 there without even knowing it. And I thought that was kind of cool. When I discovered that, I was like, oh wow, complex numbers are no big deal because we've been using them all along. So yeah, we have been using them all along. When I started digging into this and discovered, I don't really discovered it, but discovered about our really delved into it and rediscovered the complex plane, I realized that, or it was pointed out to me actually, that this is the numbering line you and we've been using our entire lives. And remember, again, we started out with 1 plus 1, 2, 3, 4, 5. We added 1. Then we added the negative numbers. So all we're doing here, it's not magic, we're just adding another dimension. We've been adding dimensions, if you will. Dimension may not be the right word for it, but we're just increasing the usability of our numbering systems. So again, complex numbers are a subset of all this. Now, how do you represent, something beyond this graphically? Well, the only way we, society, could think about it, or the mathematicians, was to add this vertical axis here, where this axis here is the imaginary part, and this is the real part. So when I say 2 plus 3i, it is right here. Now if that was 2 plus 0i, bingo, would be right there. But because it's 3i, I just could refer to the point up here. And so again, it's still what we've grown up with, but we just have a new, more depth in the number 2. We've been working on this number line. We've been working with 0i all our lives. So typically, again, it's written, and typically z is used, just like we typically use y equals ax plus b for our normal algebra, etc. But also, I noticed in some texts that we also use the order pair form. So and I've seen that in more than one, so it's something to be aware of. And what that means is if you have a complex number 1 plus 3i, sometimes in some settings it will be written or referred to as 1, 3. So don't get freaked out if you're reading about complex numbers and you start to see stuff like that in the ordered pair form. So again, it's really the real numbering line, but we're just adding this extra dimension here. And I've read in a few places that there are, that we're done. We can celebrate that the complex numbers are indeed the final set of numbers in that evolution. Maybe, because 2-3 days ago, I found some evidence that actually there are numbering systems that go beyond complex numbers. This is the problem of being a scientist, You think you're at the end, you read something else, and you're not. You still got more to go. So I'm not sure, to be honest with you, but as far as I'm concerned, all evidence I've seen in my journey of learning quantum computing, I think we're pretty good with complex numbers, although who knows, as this field evolves and as this technology develops, we might come up with something a little more sophisticated. I kind of doubt it though, because Einstein and all these guys worked on all this stuff 100 years ago, and they ended up using complex numbers. So if anybody knows that we're using anything beyond, a greater set than complex numbers, do let me know. This is a little tidbit I saw in some of my research, and Gauss was a mathematician in the 1800s, and he's the dude who really came up with complex numbers. Thank him very much. What was interesting, first of all, by some accounts, Gauss, we think Einstein's like a hero. if you took a list of geniuses in the world, there's some argument, and some people do believe that Gauss was probably the top-notch, the top dog, or the top genius ever to live in history. But what I found even more fascinating was he literally spent 50 years of his life on this topic. And as one author I was looking at commented that, hey, the dude spent 50 years of his life on it, and we may spend a month or two in school, and here we are tonight. I'm going to spend about an hour on it. So we're hanging on the shoulders of giants. And here is part of the, I want to say, confusion in the math world, as far as I'm concerned, because as we said, whether they're rational, the names of these are rational or irrational, etc. So here's another example of some confusion, unless I'm missing something. Here, we're identifying imaginary numbers as a subset of the complex numbers. So, Z is a complex number. Z equals A plus BI. And this is considered an imaginary number. This part, that's the imaginary component, and this is the real component. So if Z is a complex number, I get it, all right? I think that's pretty clear. Although, I saw this Venn diagram, and it kind of describes the situation in a slightly different way, where imaginary numbers are, intersect real numbers, and where that intersection is are complex numbers. So I can't argue with either one. It's just interesting the way they represented it in two different ways here. Maybe I'm misinterpreting a Venn diagram versus, I guess this is not considered a Venn diagram at the top necessarily. So I may be mixing apples and oranges here, but I just thought it was two interesting illustrations of the numbering systems. But imaginary numbers, kind of where they overlap with real numbers, those are the complex numbers again. So we're going from 3i to something like 4 plus 3i. All right, so let's get into some of the gory details. Now, I've seen several different ways of, several different paths when people talk about complex numbers and, the algebra associated with that, or the mathematics. It's interesting, sometimes they do adding and subtracting, then they do complex conjugates, then they do multiplication and division, etc. So there's different orders to learning this, and so I'm going to get to I guess the weirdest one, for lack of a better way of describing it, first. So before I get into addition, subtraction, multiplication, and division, I'm going to talk about complex conjugate. So complex conjugate is simply when we negate the value of B. All right, just run with it. One of the complications is we refer to the complex conjugate with two different symbols. So some folks use Z with an asterisk, and some use a bar over top of it. So I put both ways here. But essentially, if you got A plus BI, the complex conjugate is nothing more than reversing the sign of B. And complex conjugate is used all over quantum computing in the gate model, etc. So as you can imagine, when I came into this cold and I started reading stuff, frankly, I don't know if I was ever taught complex conjugate. But, like many things with quantum computing, when you drill down and you take the time to actually understand what it is, at the atomic level, as a pun, it's very simple. Complex conjugate is simply the negating of the B. Now, what's interesting, and I won't get too graphical tonight because I want to stay a little less winded than I could be on this, but let's say we had 2 plus 1i. That would be this point. And the complex conjugate is essentially where, this is I, so it's 1i here. This is also 2, 1, okay, using the, I forget the term I used. So the complex conjugate would be 2 minus 1, which is simply here. And again, I'm not going to get into all the graphics tonight. I'll say that for another day. But it's essentially, this is relevant to us in quantum computing, excuse me, we're basically, the complex conjugate is essentially flipping the point on the x-axis. So I think that's an important thing to consider. In the gate model of quantum computing, you flip things around axes all the time. And so this was an aha moment for me. I started to see, oh, that's interesting. That's something we do in quantum computing. And that is, we're essentially just negating this second real number there. Okay, so that's a complex conjugate. It's just the conjugate. The second thing, I'll take the liberty, coordinate numbering. I forget the term. I call it the order pair form here, but it could be coordinate numbering. Sounds like a fair term. I'm looking at the chat here. Important thing is, if somebody uses coordinate numbering, you understand what it means. All right, so the next thing, before we get into addition, subtraction, multiplication, division, is the absolute value. And first of all, in grade school, we're taught the absolute value of 4 is 4, so we basically are looking for, we want to drop the sign, essentially. All right, but really, the mathematicians think of the absolute value as the distance of the point on the number line from the origin. And the origin, of course, is 0, if you recall or not, right? So if I had the number 3, the absolute value is, it's 1, 2, 3 away from the origin, so the absolute value of 3 is 3. If I had minus 4, the absolute value, it would be this number here. It's 1, 2, 3, 4, and so the absolute value is 4. Okay? Now, what about a complex number? All right, so let's take the complex number 2. That's a 2 there, excusez-moi, plus, let me see, let's do 3 plus 4i. All right, let's just put that on. We want the absolute value of 3 plus 4i. All right, so if I plotted that, here's my favorite number line system I grew up with as a kid, but then I'm going to put that point here because I'm in the complex plane. So what's the distance from this point to this point? That's the definition of absolute value. Right? It used to be, back in the day, it was super easy. Now it's a little more complicated. And try to use the mouse with my left hand. It's kind of hard to do. And also I want to bring out the point modulus. I do see the word modulus used quite a bit in quantum computing. So pay attention to that. That's another one of those little things that throws you for a loop, yet it's really simple. All right, so ladies and gentlemen, what's the absolute value, or what's the absolute value of 3 plus 4i? Well, it's the distance from this point to this point. And if you remember, things like the distance from here to here is 3, and the distance from here to here is 4. 3 squared plus, and we want that value, 9 plus 16 equals 25. We take the square, of course we got to do it properly. Take the square root of 5. So the absolute value of 3 plus 4i is 5. Is that sweet? So we go back to the Pythagorean, you know the theory I'm talking about. The hypotenuse, the whole a squared plus b squared equals c squared, or as I've seen it lately, it's c squared equals a squared plus b squared. That's all we're doing here. So you basically take a squared. So the absolute value, or the modulus of z, is a squared plus b squared, and you take the square root of that. Pretty sweet. Not a big deal. I think most of us can remember this. Might be a little rusty on the Pythagorean theorem, but you know, little practice will get it back. I was at least really rusty on it, to be honest with you. I've been writing programs all my life to do this. I don't remember how to do it by hand anymore. Embarrassing, but that's true. So, so the way we could think about it is the definition of it is z equals square root of z times the z conjugate. Okay, that's the actual definition. The square root of a squared plus b squared was the way we thought about it here, in ways that most of us are accustomed to, but the actual official definition looks like that. And so you know, we're really taking the absolute value of a plus bi, and we will get into this when we get into multiplication. But I find, in my opinion, when you're first learning it, or getting exposed to it, just turning it into a squared plus b squared equals c squared, it becomes quite straightforward. But the technical way of doing it is, and it's important, by the way, to recognize it's z times the z conjugate, square root of, and that is the absolute value of z. We'll get into this in a couple minutes. Better be fast. This is 7:52 already. Holy cow. Anyway, an important point is that the modulus, aka the absolute value, is always a positive number. And notice that it's also a real number, right? Because we're talking about distance. And when we talk about distance, we're talking about real numbers. Okay, so so let's go into the four amigos, addition and subtraction, child's play. You got a plus b, I, we got, let's call it z, I think it's w that we sometimes use, I forget what it is, w, well, let's just say c plus di. So we've got, we want to know z plus w. We want to add these two. So we want to add a plus bi plus c plus di. You essentially have a plus c plus bi plus di, which is essentially a plus c plus b plus di. So I hope I didn't trivialize it too much, but it is pretty trivial. Essentially what you do is you add the real components, and then you just simply add the imaginary components, and it's quite simple. So if I had 4 plus 2i plus 3 plus 6i, we add these two to get 7, and we add these two to get 8. No big deal there. If I were to add these two imaginary numbers, minus 3, minus 6 gives me minus 9, minus 1i plus 7i, because the minus and minus, and I get 6i. 1 plus 16, don't forget we got the subtraction, I'm doing addition and subtraction at the same time, gives us 17. 4 minus 9 gives us minus 5. Any issues there, folks? I'm trying to make this interactive, but it's hard when you're, A, when you're a rambler, B, when it's math and you can't use math. Questions about math in chat are kind of awkward. I'm going to assume we're okay there. All right, multiplication. This is, at least in America here, this is how most of us, I think, learned it in the United States, the first, outer, inner, last. So we have just in normal algebra, equals A times C, so the first, then the outer, then the inner, frankly, now that I think about it, you younger folks probably do something completely different. This probably just shows my age because this just sounds so ancient. But this is the FOIL method. I don't know if they teach it in school anymore. But it's essentially the same thing with complex numbers. Although it does feel a little tricky when you first do it. Of course, silly me, I put large numbers in here just to make our world more complex. But here, if I do first, that's 4 times 12. First outer, so that's 4 times 11i. Inner, that's minus 60i. Correct me if I screw up here. Actually, I should be writing, hold on, I think I can use back. Sweet. So this would be minus 5 times 12. Whoops, minus 5i, oh boy. Times 12. And then last, so plus minus 5i times 11i. Okay, let's simplify this a little bit. That's 48 plus 44i plus minus 60i plus, geez. So what is this? So this is, you could think of minus 5 times 11 times I times I. Okay. And so this becomes minus 55. And this, what I times I becomes, ladies and gentlemen, first one to put it in the chat wins a t-shirt. What's I times I? Going back to a couple minutes ago. Come on. Bingo. David, if I had t-shirts, you would get it. Because the square root of minus 1 times the square root of minus 1 equals minus 1. So now I've got 48. I'm going to combine these puppies here. So that's minus 16i. Is that correct? And then here I've got minus 55 times minus 1. So that's plus 55. And so we got 103 minus 16i. Yippee. All right. I don't know about you, but the first time I saw this in 20 or 40 years, I was like, oh, wow, that's cool. So it's a little nuanced here, but really the main message here, the main story is that, you know, what's unusual, what's different here is you're taking the last components, which is the minus 5i times 11i in this particular case. You're getting minus 55 times i, and which means this is becoming minus 1, and so minus 55 times minus 1 becomes 55. So that's the little nuance, nothing more than the FOIL method, things that we've known all our lives. All right. Ain't no freakiness here. Now division, let's get freaky. All right. So 7 minus I divided by 2 plus 10i. All right, I got the answer here for us. Anybody have a guess? How do you do this? Well, multiply it by 1. Duh. Oh, I have the answer right here. Silly me. All right. So you multiply the denominator with its complex conjugate. The I goes away. Woohoo. So what we're saying here is, I'm going to multiply this puppy by 1. Simple. Huh? What's that going to do? All right. Well, you can tell I'm starting to get a little giddy here, so it's probably going to be a little more entertaining. But wouldn't you say 2 minus 10i over 2 minus 10i equals 1? If anybody disagrees with that, please say so on the chat. And you will owe me a t-shirt. Anybody? Anybody disagree? So, all right, well this is 1, so you multiply any number times 1, you get the same number, so no big deal. But, so what we end up with is 7 minus I, let me put this together here, times 2 minus 10i over 2 plus 10i times 2 minus 10i. Remember this, and the trick here is this is the complex conjugate. That's why I told you about the complex conjugate. Comes in handy when you're trying to divide. All right, well, first in or out or last. Well, these are terrible twos. So first in or out or last. So 4 inner, no. First outer, yes. Phew, it's freaking out. So this becomes minus 20i inner. This becomes plus 20i. Anybody see it? And then last, this becomes plus 100. Anybody uncomfortable with the 100? So, awesomely, this becomes 0. So, this becomes 104. And keep in mind that's at the bottom. I hesitate because it's not matching my answer, so I must have done something wrong. That's squared plus, yeah, that's right. Ah, why not multiply by the conjugate number of the numerator? Well, that's a good question. Why not multiply by the complex number of the conjugate of the numerator? What would that do? Well, see, we would still, wait, let's finish this and you'll see why it's so beautiful. So this would be 14 first outer minus 70i minus 2i. So that's what is this? It's 10. So that's minus 10, I think. This becomes 4 minus 72i. And so 4 minus 72i over 104. 4 over 104 minus 72i over 104. Yeah, I'm not going to take our time to figure that one out. Oh, hell yes, I will. So 4 becomes 1 over 26, and 72, so 8 divided by 8. Yeah, so divide this by 8, you got 9 over 13i. So why not multiply it times the numerator conjugate? Try it. And I think what we'll end up doing is we'll be making, if you multiply the numerator times the conjugate of the numerator, then we'll have a real number on the top and an imaginary number down at the bottom, which is just as confusing. But I guess you could, right? So it would be r over a plus r over b. See, but then you got the square root of -1 down in the denominator, and you're gonna have trouble plotting that, because what we want is a plus bi form, although r over bi. That's a good question. Who asked that question? Himek. All right. You got some homework. I got some homework. Thank you. Yeah, because no, we're still stuck with 1 over I. Right. So yeah. So if you had 1 over I, how do you plot that? You can't. You got to get this puppy out of there. You can't have 1 over I and put it on this plane. Wait a minute. Where's my head? Yeah, so that's why we don't want to do it. Hold on, I'm trying to get back. Ooh, that looks freaky. There we go. Yeah, okay, so the question is, if you have 1 over I, oh man. Next thing you know, I'll get the blue screen of death. It's magically disappearing. Yeah, so you wouldn't be able to plot that. 1 over the square root of -1, we can't plot it. That would be my excuse. Anyway, I think the clock's on my side here because I'm just going to wrap up. So I grabbed some stuff. I thought about it and I said the easiest and then probably the best is just grab some stuff from existing material when it comes to Python and complex numbers. So I have a subset of the material from 2 websites. Let's just walk through it quickly for those of you who are familiar with Python. Just because, you know, it is important if you're going to be using Qiskit or any of those programming tools. So the trick is in Python, you need to use J instead of I. And I read somewhere, yeah, here it is, because in engineering, they use J rather than I. I means something else in electrical engineering. I'm still lost the rest of it here. But so that's one gotcha if you use Python. And if you say 1J, it'll know what the Python compiler know what you're talking about. So here's an example of 1J times 1J, which is the same as I times I. And here you go, right? You get the -1. Wow. My writing doohickey here now, whenever I write something, it disappears. Is that nasty or what? Okay. So that should make sense, right? I squared equals this bizarre. I squared equals -1. This is like that chat thing, you know, when you send it, or that picture chat, Twitter, whatever it is, it disappears after 10 seconds. Oh man. Okay, but here's one of the ways that the 2 plus 3. Oh God. So 2 comma 3 means 2 plus 3J, which means 3I. So it's built in. So if I had a real number, Z, I'd say Z is assign the value of 2 plus 3J. I could say, what is the real component? And it'll say the 2. And what's the imaginary component? It'll indicate the 3. If I want to conjugate that, I think my laptop is, I think it's telling me it wants to crash. Something odd's really happening. It's not, the graphics are just dying. It's a local problem. I think I'm running out of memory. Okay, anyway, look folks, it's getting late. I'm getting giddy and you probably had enough. So I'm glad I kept it to the minimum because I could probably go on for 3 more hours. I had a lot more material planned, but there we go. Now I grab it. Anyway, next steps, next time maybe, if feedback's okay, but there'll be a next time. Otherwise, next steps, anybody, my recommendation, what I'm finding is we'd need to brush up a little bit on trigonometry, and it's just simply understanding sine, cosine, and arctangent. Tangent, remember tangent, the arctangent is you just flip the numerator and denominator, but those are things that pop up. Then the next thing after a review of a little bit of trig, just a tiny little bit, then get into polar coordinates, which are really important as you may think of the Hilbert or the sphere. And then some of the special numbers. E pops up, obviously, if you haven't seen it yet, you will, pi, and those sort of things. So those are things that would recommend as next steps here. Are there any questions that I can hopefully answer? Or respond to. I don't know if I'll answer it. Let's see what we got here. Yeah, so what I'm going to do, going to save. I just saved it. So I will publish this in the usual spot for meetups for Harrisburg, and that would be here, I'll put it in chat. So it's harrisburg.tech.meetups.200521. Let me just check real quick before I post this. 1 second. I don't want to give you that typo. There we go. So it'll be in that site in the next half hour. That's where I'll put this document. Yeah, it's to the place where I post stuff from previous days. Find a list of meetups. Oh, hello. Wow. So Quantumapalooza is a site that consolidates a lot of the meetups. Yeah, that link is not found yet because I haven't created it yet. It'll take a minute. In fact, if you want to wait a minute, I'll create that link for you. And so one feedback is it should spend more time on the basic, on the more focus on the fundamentals. Yeah, I can see that. I think, yeah, I rambled too much, obviously, but from my view, the understanding the story there is something that you won't read about. And so that's what I can bring to the table. I like to believe. So anyway, ladies and gentlemen, I just added the location, and you know what? I'm just going to put this file out there right now. 1 more second. Okay, so that file's out there, ladies and gentlemen, the document's out there. Yeah, anyway, so where I was going with that, you know, the story that I told you, I think is important context for understanding complex numbers. It's not something you can get from one source. I think after tonight, you should be prepared to just you know, randomly go to Google and look up complex numbers and, you know, get some practice in the addition, subtraction, and stuff like that. I think so what I try to do is tell you stuff that you just can't pick up a book and follow. hopefully if you understand the context and you get this little preview, you can pick up a book, or not even a book, just an article on complex numbers and follow it. That's what I'm hoping you take away from that, from this. And I'm not trying to reproduce what you can get in a book easily, but I think hopefully if I made any sense today, you understand the context of complex numbers. You see it's not that difficult at all, the algebraic aspects of it. It'll get more trickier when you get into the polar coordinates, something that are very important. But I'm pretty confident you guys could go to a website and get the algebraic aspects pretty quickly right now. Anyway, let me see. So QC meetups, good refresher. Yeah. I hope the Quantum Palooza site's up. Let me see, that's working good. Where the slides are, you got it. A list of meetups, future, yep, go to Quantum Palooza. Not found, I'm catching up. Yep, there you go. Index of meetups, you got it. Today's February 21 or May 21. So I think, did I put it on the wrong date? No, I got it in there. Lionel, did you find what you're looking for? Yeah, I got a t-shirt for you, man. I shouldn't say stuff like that. One of these days I will have t-shirts, but all the t-shirt places better be closed. All right. Any other questions? All right. Well, thanks, folks. I appreciate your attention. I learned a lot because I tell you, like I've said before, if you ever really want to get intimate with some subject, try talking about it and you'll find that you learn even more. So I learned probably more than you did tonight as I tried to explain this to somebody else, which is a segue into if any of you would like to give a presentation. You don't need to be a PhD. You don't need to be an expert, but give a presentation and talk out loud and share what you're learning with other people. Let me know and we'll get you set up. Thank you, Helen. Anybody, we never recognized Helen Ma, but she's a goddess in disguise. And speaking of that, I need to put the slides back on. So Association Quantum has their next event is on the 27th, and it's daytime, which is unusual for most of us. I think those guys are starting to have more daytime content, myself included. But we'll have a nice history of quantum. I'm sure that goes way back. It's 100 years worth at least. Then Doug Fink, who runs the Quantum Computing Report. Great guy, he's been around quite a while. If you don't know about the Quantum Computing Report, look it up. But it'd be good to hear what Doug has to say about the ecosystem. If anybody understands the ecosystem, he would definitely be in the top 5 for sure. And then Andre Koenig, great guy, really takes the business aspects of quantum computing. By the way, he started a weekly show on YouTube that you may want to dial in on. I don't put it in Quantum Palooza yet because I haven't figured out his broadcast schedule, so I can't put it on a calendar. But he has a weekly conversation anywhere from 15 to 20 minutes long is their target on things that are going on in the quantum computing space. So he runs that show. Anyway, he'll be the guest of the Washington Quantum Computing Meetup on June 16th, which is a Thursday night. Let me see, blah, blah, blah. What about discussing problems from the end of the chapter from QCQ book? QCQI book. What was some problems from the end of the chapter of the QCQI book? Wait a minute, I'm lost. Wait a minute. Quantum computing. Lionel, fill me in. Yeah, it would be of interest because I can't think of what the QCQI book is. Oh. Yeah. Yeah, so that's a great idea. I mean, Lionel, if someone wants to take a chapter from a book, yeah, the Mike and Ike book, Nielsen and Chang, and you want to take a chapter out of one of these quantum computing books and present that, we do that in graduate school all the time. That's a wonderful idea. And, you know, I could easily, I don't want to blow it out of proportion, but that would make a great series topped with, you know, we'll get Ike and Nielsen to maybe join us for the grand finale. Those guys are still around, obviously. Chang's up in at MIT. I don't know where Nielsen is. Nielsen actually has a YouTube site, which I highly recommend if you guys haven't run across that. Give me a second here and I'll bring it up for you. Mike Nielsen. That's the wrong one. There he is, Michael Nielsen. This is him teaching you quantum computing. Awesome. And you know, the funny thing is, if I remember correctly, the number of views are ridiculously small. Yeah, only, you know. The last two videos, we've seen there's two postulates. It's you know, Mike and Ike. So definitely take a look at his YouTube videos. I've gone through them a couple of times. They're very helpful. Anyway, I think that's it. There's still some of you out there. Anything anybody want to talk about? I'll take mute off. I'm getting tired of talking to myself. Get really giddy. But also while I'm at it, let's take a look at Andre's website. Andre's YouTube. Andre. Koenig. Yeah, here. So yeah, so he's got this weekly, started it 2-3 weeks ago, where he talks to two people or three. The last week he had 3 guests on, but he's got 2 regulars, and they're 15-20 minutes, and they just chat a little bit, and you get some really good tidbits about what's going on. Very good, useful. See you, Jim. Thank you. Very good. Andre's talk will be Tuesday. Thanks, Helen. June 16th. Yeah, Helen, you see that? Got to fix that slide. Quaternion algebras over number fields are useful for creating compiler for a okay, thanks for the tip. Institute for Advanced Study, on it. Yeah, see, I don't know what quaternion. I think these are the things that actually are a superset of complex numbers. Thanks for the tip here. I'll have to watch it. Wow, the 30 of you are still here. Is there anything I could we can do here? Ask more questions. So the artifacts are on the meeting or the doc. So the artifacts which is the word I'm using for tonight, are here, and the artifacts will be, well, already I've got that Word document that I wrote on, and then when the recording is done, then I'll have a link to the recording on that. Not that you want to watch this again, but just in case. Let me see, what else? How can I fill the airtime here? There's still some of you out there. I think we better call it a night. But but before we do that, any questions about complex numbers that I can go over again? The real interesting stuff with complex numbers, in my opinion, is when we get into the polar coordinates. That's where it gets really fun. And then it becomes much more applicable, obviously applicable to the quantum computing. All right, you guys have quieted down. I think cocktail time is over. I'm going to stop sharing. I'm going to stop here and say good night, everybody. Good to see you. Thank you, Helen, for all your support. Good night.